In this lecture, I want to continue on with the discussion of the Generalized Maxwell model and finish it up. So let me begin by just reminding you where we had ended up with on our previous lecture. So we had developed the governing equation in Laplace transform space. So let's just say previously, and that's in the last lecture, we showed the following for the Generalized Maxwell model. We showed that it could be written as a coefficient that was the sum from I equals 0 to n, where n is the number of Maxwell elements in the Generalized Maxwell model, times p sub I times s to the I, right, times sigma bar, which is just the Laplace transform of the stress. That's equal to the sum from now I equals 1 to n of q sub I s to the I times epsilon bar. We'll call that equation 1. Of course, we derived that in the last lecture. I'm not going to do that again. The key feature here to remember as we're trying to now get it back to the time domain is that these terms in this side they're all polynomials, right? Which are, it's very convenient for us then to look up the inverse Laplace transform of these polynomials. So let's go ahead and take the inverse Laplace transform. So taking the inverse Laplace transform, we'll just say LT for Laplace transform. Here's how we're going to do that, but I want to just give you an example of a single term before we write the general case. So let's go ahead and consider a single term in the polynomial. In the polynomial, let's go ahead and choose I equals 3 on the left-hand side. Let's look at that term, and that term is just going to be P3 S cubed sigma bar, right? That's what that term is going to look like. And we can take the inverse Laplace transform of that, right? So the inverse Laplace transform, we just looked that up from the table, but we also talked about it in the lecture on Laplace transforms, right? That looks like, so we can just take the P3 out because it's a constant, and then the S cubed times sigma bar, we can look up from our table is the third derivative of sigma with respect to time. Okay? So that's the inverse Laplace transform of that term. We can do that for all the terms in the polynomial. So now we can actually easily take the inverse. So for the general case, right, of the inverse Laplace transform of 1, we can write that. Let's see. So we're going to need to say that this, here's our bracketed term, and there's our summation from I equals 0 to n. And now a pi, that doesn't change, right? That's just a constant. And so the term is s to the I power times sigma bar, and that just becomes the ith derivative of sigma in the time space. So this becomes the ith derivative of sigma with respect to time. Okay? I don't even need to put this in brackets. Okay? There we have it. And on the other side, we get something very similar. Remember, this one side only goes from 1 to n, and it's going to be q sub I times now the ith derivative of epsilon with respect to time. Okay, let's call that equation 2. Let me expand this out for you, just so we can kind of look at what the terms are doing here. So we have p sub n, and I'm going backwards now, the nth derivative of sigma with respect to time, and then we can go to the n minus 1 term, and now this is the n minus 1 derivative of sigma with respect to time, okay, plus dot dot dot. Then we have, let's say, P1, which will be just the derivative of sigma with respect to time, plus P0 times sigma. Okay? And then we'll give you, that equals, I'm going to write the left-hand side below it here. That equals, now q sub n, the nth derivative of epsilon with respect to time, plus the same thing now, n minus 1, the nth derivative minus 1 of epsilon with respect to time. Oops, I better put an n here and an n minus 1 here. And then dot, 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 plus finally q1 partial epsilon with respect to time. Okay? So what we want to do now is a gut check, right? So let's just say as a check, just a reality check. Okay? Let's just choose n equals 1. Let's just try that because we know what the solution is supposed to be, right? This is always a good thing to do. Make sure you recover the known solution. Okay, and if we try n equals 1, what we're left with is P1, the partial sigma with respect to time, plus P naught times sigma is going to be equal to Q1 times the partial of epsilon with respect to time. Let's write that in the form that we've been writing it, which says P1 sigma dot plus P naught times sigma is equal to Q1 times epsilon dot. Okay? And what do we find that is? That is the governing equation, right, for a single Maxwell element. So it worked out. Now, of course, you can look up what P1, P naught, and Q1 are in terms of the E and the eta for that element, but the idea is that this recovers that equation. An item of note also in this, if you look up back to equation 2, is that, so here we go, there's a note. What happens as I add additional Maxwell elements? Well, if you can see as I go, if n equals 2 now, and I look at that equation, I see that for every element I add, I increase the order of the governing differential equation, right? So, so for each additional Maxwell element, okay, so for each additional Maxwell element in the generalized Maxwell model, the order of the governing differential equation is increased by 1. Okay, so the order of the governing differential equation is increased by 1. Okay? Something that you might be wondering, if you remember back to the construction of the generalized Maxwell model, we put all of these Maxwell elements in parallel. And so you might be wondering, well, what happens if we put them in series? So I'm not going to derive it, but I'll just tell you. Okay, so it can be shown, which means maybe I'll use it as a homework problem or something, but it can be shown that Maxwell elements in series, okay, Maxwell elements in series behave exactly like a single Maxwell element. Behave exactly like a single Maxwell element, so there's no need for them. So let me tell you how you would get it. If you had a bunch in series, then what you'd end up doing is you would write, you'd choose a single Maxwell element where E was given by the sum from I equals 1 to n, where these are your Maxwell elements, of 1 over E sub I, and then you'd take the inverse of that. And similarly for eta, if you created a Maxwell element, a single Maxwell element with these values of E and eta, you would recover whatever the series solution that you just tried to create was. So as a result, we don't use Maxwell elements in series because there's no point in it. It doesn't give us any advantage. Let me give you a few concluding remarks. Okay. Number 1. Okay, if an element in the generalized Maxwell model is supposed to be a pure spring, then we set eta to infinity. And if it's supposed to be a pure dashpot, then we set E to infinity. Okay? So if an element, okay, in the generalized Maxwell model is supposed to be a pure spring, right? Then we set eta goes to infinity, and if it's supposed to be a pure dashpot, okay, then we set e to infinity. So we can use we can accomplish anything that we want in terms of springs and dashpots in that model by just setting those values to infinity if we want to go to a pure spring or a pure dashpot. Okay. When do we want to use a generalized Maxwell model, right? Because we also talked about, or maybe you're going to assume that there's going to be a generalized Kelvin-Voigt model, which there is. So when would you maybe use one over the other? In the case where strain history is prescribed is when you're going to want to use the generalized Maxwell model. So if strain history, okay, so that's the kind of the trick that suggests you might want to. So if the strain history is prescribed, the generalized Maxwell model is more convenient. Okay? Doesn't mean it can't be used elsewhere, but it's just more convenient. It's more convenient than the generalized Kelvin-Voigt model, which we haven't talked about yet. Okay? And the generalized Kelvin-Voigt model. All right. And then finally, going back to the reason that we created this generalized Maxwell model, it actually represents real materials better because real materials show a spectrum of relaxation times, and a generalized Maxwell model can better approximate that. So just say the generalized Maxwell model better approximates real materials because it can simulate multiple relaxation times. Simulate multiple relaxation times. Okay, which of course better match the spectrum of real materials. I'll just call it the relaxation spectrum of real materials. Okay? So that's all I really want to say about the generalized Maxwell model. It's a very versatile, and it lets us sort of tune our model parameters by just adding additional Maxwell elements to try to capture more realistically the generalized material behavior.